This is lesson 14 of the No Frills A-level physics lessons, and this one's all about energy levels in atoms. Now, the first thing to remember is the reason why electrons stay within atoms at all is because if they didn't, the atom would become a positive ion. And then that positive ion would attract the electrons back. The model that we can use to describe what's going on in an atom is a very straightforward, almost a planetary model, where we have the nucleus and we have the electron. The electron's happily orbiting around the nucleus in a circle, but the nucleus and the electron are attracted to each other because of the electrostatic force. That's what's happening. Now, in attraction, and I'll put in brackets there, electromagnetic. Now, we've already looked at that, of course, the different forces earlier on in the course. And we know that the electromagnetic force acts between all charged particles. And we can use an analogy and say it's just like planets attracted to the sun by the force of gravity. But there's a real difference here, a distinction between what's going on with gravity and what's going on within this atom. Because with gravity, the planets can be anywhere. And we can have asteroids and comets and all the rest of it. And we could have spacecraft that are released from the planet Earth and make their way towards, pick a different place in the solar system or beyond, not very far beyond, but a little bit. We can talk about that because the spacecraft is able to exist anywhere within the solar system. But that is not the case for electrons in atoms. There are only certain energy levels that the electrons can have. And so this is a difference between what's going on with gravity and planets. So only certain energy levels an electron can be in. Something like that, I might say. Only certain energy levels the electron can be in or on. Certain shells, we call them, where the electron can be, or certain orbitals, sometimes it gets called. And you've already learnt this in chemistry. If I start constructing our picture of the atom from what we learnt in chemistry, then we have, and this is chemistry GCSE, then what do we have? Well, we have a nucleus in the middle, sure, okay. And then we have an electron shell which has 2 electrons in it. And then we have another electron shell. Let's do a better job of drawing it. We have another come on, pen. We have another electron shell that has 8 electrons in it, or a maximum of 8, I should say. It doesn't have to be 8, it could be fewer than 8, but it cannot be more than 8. And then we have another shell, and this is where people start getting a little bit scared, because we might say that this is 8, which in a sense is true. When we've got 8 electrons in that third shell, we start putting electrons in the fourth shell, but actually the third shell isn't complete. Now we could put up to 18 electrons in that shell. So that is a little bit more complicated than what we learn. Why is that? Why do we start filling the fourth shell when the third shell isn't complete? Because of what we call subshells. Now, why is it that we can only get 2 electrons in that first shell? We can only get 2 electrons in the first shell, so 2 electrons in first shell because they are fermions. And you may remember what fermions are. They are fermions. So fermions are a class of particle where they cannot exist in the same quantum state as each other. So 2 electrons cannot have all of the same quantum numbers. It's just not possible. And what are those quantum numbers? Well, charge, and the electrons have the same charge. What we call the principal quantum number, that is the energy level, So N equals principal or pal? You see, I always get confused with this. And it's not something that appears in the A-level specification, the terminology of principal quantum numbers. So principal, I feel like it should be AL, but if it's wrong, someone get in the comments and tell me I'm wrong. Principal quantum number. I run out of room. Quantum, don't have enough room on the edge there. Let's just write it underneath. N equals principal quantum number. I'll write it like that. It's only note taking. So we've got charge, we've got principal quantum number, but there's also spin. Now, spin, there are two possible states. We call them spin up and spin down. Two possible spin states. And because of that, we could have an electron where n equals 1. That means it's in that first shell. It's got the charge of the electron. It's got, all the other quantum numbers are the same, but one of them is a spin up and one's a spin down. That's what we call the two different spin states for the electrons: spin up, spin down. So if that's true, why can we get 8 electrons in the shell with the principal quantum number n equals 2? Well, that's because there are different shell angular momenta quantum numbers. This is where it gets a bit complicated. Now, you might have seen lovely diagrams for our atom where we have the nucleus in the middle, and then the electrons form clouds. And maybe we have a first cloud, that's n equals 1, the second cloud, but then you might get clouds that look a bit like this. And obviously there's one coming towards us and away from us as well. And then there's even more exotic clouds. So what's going on here? Well, we have 3 different orientations of these, what we call lobes, these interesting shaped clouds. One orientation is vertical, one orientation is horizontal, and one orientation is towards us and away from us, in and out of the page. So we have our spherical shells, and each spherical shell can have 2 electrons, one spin up, one spin down. But then each of these polar shells, these lobes, and there are 3 different ones of those, each of those can have 2 electrons, one spin up, one spin down. So that means we have 2 electrons in this shell, 2 in that shell, but we have 2 in this shell, 2 in this shell, and 2 in the shell that goes towards us and away from us. Now, they are all energy level 2. They're all n equals 2, not the first shell. Let me change the color of the first shell, perhaps, so that we're not going to get confused. Let's make the color of the first shell blue or something so we can see the difference. There we go. There's our spherical shell here, which has 2 electrons in it. So the blue one is n equals 1. The green ones are all n equals 2. And so you can see we've got 8 electrons. And the next shell, n equals 3, has a spherical one with 2 electrons, has those polarized lobes, so there's another 6 there. And then it's got something more exotic, which is actually a higher energy. So we start filling the 4th spherical shell before we've finished filling the 3rd shell entirely, because of these what we call subshells. I'll put that in brackets. Now, I went a little bit off topic there because that isn't actually on your your A-level physics curriculum, but it's interesting to know about. Now, the electron cannot, back to what's important, the electron cannot exist between these shells. So if we give electrons enough kinetic energy and then collide with the atom to cause excitation, but not enough energy to cause ionization, then the electrons that are bound to the atom will only remove energy equal to the certain amount. When we say an atom is in the ground state, what we mean is that we are starting from the lowest energy level and filling up electrons up to how many electrons we've got, so that there's no way that any more energy could be taken out of that atom. And we can excite the atom by putting energy into the atom. And in doing so, that excited atom, inside it, the electrons, one of the electrons, more of the electrons, will have moved up an energy level. And that's really quite important to realize what's going on there, because the electrons are part of the atom. They're not just in the atom, they are a part of the atom. So we can quite correctly say that the electrons move up an energy level and that the atom becomes excited. Fine. Now, we can measure the excitation energies, and we've talked about measuring the excitation energies. So what's going on there? Well, let's draw an energy level diagram, and let's do it over here on the left. Energy level diagram. We could do an energy level diagram for the electrons. Where are we after? A straight line. An energy level diagram for the electrons that are in an atom. And I'm going to take something very straightforward like hydrogen, but we could look at mercury as a common one that gets looked at as well. And we have the n equals 1 all the way down there. And then we might have n equals 2, and then we might have n equals 3, and then we might have n equals 4, and then we might have n equals 5, and so on, all the way up to, they get closer and closer together, all the way up to n equals infinity. And this is a diagram where the vertical axis is energy. So for our hydrogen, we have a special formula to calculate the energy of an energy level. Or should I say, the energy that we would have to give an electron in, if it was in that energy level, for it to escape. So what we've got here is n equals infinity. Down here we've got n equals 1. Remember, n is the principal quantum number, however you spell that. N equals 3, n equals 4, n equals 5. And there's actually a clever equation that we can use to determine the energy of the electron, or the energy we would have to give an electron at that energy level to get it to escape. Now, this equation is not required for your A-level, but I will give it to you anyway because I think it's interesting. It is that the energy is equal to 13.6 electron volts divided by the energy, the principal quantum number, squared. And that's only for hydrogen. This is important. It's only for hydrogen. So let's put for hydrogen. So if we use that equation, we get some energy levels. Let's pop them down here. For hydrogen, this is going to be 13.6 electron volts. What do I mean by that? I mean, I have to give the electron 13.6 electron volts for it to leave the atom. Fine, okay. N equals 2 means I do 13.6 divided by 2 squared. 2 squared is 4, so that's 3.4 electron volts. I have to give an electron. If the electron was in this energy level, in order to get it out, I have to give the electron a minimum of 3.4 electron volts. Any less than that, and the electron won't come out of the atom. So the atom will not become ionized. For n equals 3, it is 13.6 divided by 9, and you get something like this electron volts. And we could do 4. Remember, 4 squared is 16. So 13.6 divided by 16 is 0.85, and so on. And they get closer and closer together, the differences. Now, what we say is that the electron that escapes, its kinetic energy is going to be equal to the energy it was given when it was bound to the atom, minus the energy that had to be taken away from the electron to get it out of the atom. Not the ionization energy, because remember, that's the minimum energy to make an atom into an ion when the atom's in the ground state. But if I have an electron that's sat in n equals 1 and I give it 14.6 electron volts, then 13.6 electron volts is spent getting that electron to n equals infinity. And the electron leaves with 1 electron volt of kinetic energy. If the electron was in the n equals 2 state, and it had 3.4, I gave it 4.4 electron volts, then it would spend 3.4 electron volts getting to the n equals infinity state, and the electron being unbound, and it would carry 1 electron volt of kinetic energy away. Now that's interesting, because the 2 electrons I've just described both have the same kinetic energy once they've left the atom. Once they've left the atom, they're going their own way. They don't care what's going on with the atom anymore, or the ion as it would be. They don't care anymore. They're doing their own thing. So those 2 electrons are identical to each other. They're indistinguishable from each other. And yet I gave one of them 14.6 electron volts, and I gave the other one 4.4 electron volts. So how am I going to reconcile what's going on here? And the way we do that is by we say that the energy level has a negative energy, like this. So at n equals 1, the electron sat there has negative 13.6 electron volts. So if we give that electron 14.6 electron volts of energy, then 14.6 plus negative 13.6 is 1 electron volt. Whereas if our electron was in n equals 2 and we gave it 4.4 electron volts, it already has negative 3.4 electron volts. So 4.4 plus negative 3.4, that's going to be equal to 1 electron volt. And I could just quickly write those down. Just 2 cases just to have a look at. We've got electron that starts in A and an electron that starts in B. So in case A, imagine that we have, we give 14.6 electron volts. Then what we've got is 14.6 plus negative 13.6 equals 1 electron volt of kinetic energy. And in case B, perhaps we give an electron that's in that place, we just give it 4.4 electron volts. When I say give it that energy, that's a bombarding electron colliding with that bound atom, transferring kinetic energy. And it happens to transfer 4.4 electron volts, then that's going to be 4.4 electron volts plus the energy it already had, which was negative 3.4, and that gives us 1 electron volt of kinetic energy. And so now you can see that the only sensible thing to do to make this work, to make electron A and electron B have the same 1 electron volt of kinetic energy when they've left the atom, is to have the electrons when they're bound expressed as having negative energies. And that's what we do. So that's an energy level diagram, and it's quite a useful thing to use. Some terminology then. We have excitation, when an electron moves up an energy level. We also have de-excitation. Sometimes it's called relaxation, but I don't like that. De-excitation, not dexitation. That's when the electron moves down an energy level. When the electron moves down the energy level, we have de-excitation. Now, you can only have de-excitation if there's a space for the electron. So if you look at the picture on the right, with all those different interesting shells, or even if you look at the picture on the right at the top, the more basic version, the Bohr model of the atom, which is the one on the top right. In fact, let's label that as Bohr model. And this one here is the Schrödinger model. So you can see, if you take either of those models, If there's a space for the electron to fall down in energy level, then it can do, and that's called de-excitation. The electron moves down at an energy level. Only if there is space to do so. And there's only space to do so if there's a missing electron there. Why one electron, and so on and so on? It's because they're fermions. It's what it says at the top of these notes. And because you only get 2 electrons in each subshell, and that's because of the 2 different spin states of the electron. What is spin? Look it up. It's way beyond our A-level curriculum. So that's de-excitation. Now, what happens when we have de-excitation is the emission. This causes photon emission. And the energy of the photon, E of the photon, which is equal to HF for the electromagnetic radiation, is the de-excitation energy. We could say the excitation energy. De-excitation energy. When the electron moves down an energy level, the atom is de-excited. It's moved from one energy level to another. That amount of energy that's been released when the electron moves down is released from the atom as a photon with a particular frequency. And we'll be talking about the spectrum of those photons and how that relates to energy levels in next lesson. But what that means is that if we have, let's say, B to A, a transition from B to A, using the diagram above, well, that's going to be, in our case, negative 3.4 subtract negative, because we subtract the 2 energy levels, negative 13.6. So we go from B to A. So if we do that, we end up with a photon with 10.2 electron volts of energy, which we have to convert into joules. So we can say that 10.2 electron volts multiplied by 1.60 times 10 to the negative 19 joules per electron volt gives us the total energy of that photon in joules, which is, let's just type it into my calculator, 1.632 times 10 to the negative 18 joules. Okay, and what's that as a frequency? Well, the frequency is going to be that divided by Planck's constant, times 10 to the negative 18, divided by Planck's constant. The Planck's constant is 6.63 times 10 to the negative 34. So 6.63, I'm typing it into a calculator, you can't see that. I'm typing it into a calculator off screen. And you get 2.46 times 10 to the 15 hertz. And we could work out what the wavelength is for that by using C equals F lambda. So therefore, lambda is equal to C divided by F. So we know that C is the speed of light, 3 times 10 to the 8. That gives us about 122 nanometers. So light that's emitted from that transition from the second energy level to the first energy level in hydrogen, we can't see it. It's invisible. It's part of the infrared. No, sorry, it's part of the ultraviolet. Whoops, sorry, I said that wrong. It's part of the ultraviolet spectrum. Now, we do use that ultraviolet light. We can use that for something that's called fluorescence. It's very clever how fluorescence works. It's not just electrons that can transfer energy to atoms. Photons can as well. So fluorescence is one of these interesting phenomena where a high energy photon, or it's a higher energy photon, is absorbed, and two lower energy photons or more are emitted. So Just make a little note of that. High energy photon absorbed, 2 or more lower energy photons emitted. So how does that work? Well, let's just think about our energy level diagram. We've got perhaps the atom in the ground state down here, but then we might have excited states here and here. Excited states that the atom can be in. So let's label this one as ground state. And these are excited states. Excited states. Now, in the first instance, we've got an electron that gets moved to a higher energy level. So the atom moves into an excited state. And that happens when a particular energy photon is absorbed. So here we have HF coming in and being absorbed. Absorbed by the atom moving an electron into a higher energy level, so the atom is in an excited state. But then what happens? Well, it could have the atom drop straight into the ground state again, and if that happens, we will get exactly the same energy photon emitted. That can happen. That's not fluorescence. Now, with fluorescence, what we have is the second option in the way of drawing these energy levels, which is that the electron does not fall straight back down to the same energy level it was initially in. No, we could have the electron move up into a higher energy level due to the atom absorbing the energy from the photon. So that can go like that. And then the electron can drop down in 2 stages, like that. So now we have the energy coming in, HF absorbed. But now instead, we could have, let's go with orange or something, lower energy. We could have 2 photons emitted with lower frequencies each. Let's go with a yellow one as well. Like that. So the photons that are emitted here, these emitted photons, are each lower energy. Lower energy than absorbed photon. Now, this is very useful. We use this in fluorescent lights. For example, energy-saving lamps. We use a mercury vapor, and what happens is the mercury vapor will get excited, and when it de-excites, it emits ultraviolet radiation. So we have these high energy photons. But then we coat the inside of the glass vessel that contains the mercury vapor. We coat it with a white powder, some sort of mixture of phosphor compounds, I don't know what, I'm not a chemist. And that causes fluorescence. Those compounds will absorb the UV photons, and then they will emit photons of lower energy, just like you can see in this diagram. So that's fluorescence. And that is as far as I really want to go in this particular topic. So next lesson, we'll be looking at energy levels and actually the spectra of light that's produced from those electrons moving down energy levels. So we'll be dwelling a little bit more on this idea of emitting different energies of photons in the next session.